because obviously artists and designers use the color space to explore.
Sure. No, I mean, it's just an example of kind of how do you, the typical person, how do you describe what a color is? Oh, well, there are these numbers that describe what a color is. Well, it's worth, if you're an 8-year-old, you won't necessarily know, it's not something we're born with to know that, colors can be described by 3 numbers. That's something that you have to, it's a thing to learn about the world, so to speak. And I think that, that whole corpus of things that are learning about the formalization of the world or the computationalization of the world, that's something that should be part of kind of standard education. And, there isn't a course, a curriculum for that. And by the way, whatever might have been in it just got changed because of LLMs and so on.
Significantly. And I would sort of watching closely with interest, seeing how universities adapt.
Well, so one of my projects for hopefully this year, I don't know, is to try and write sort of a reasonable textbook, so to speak, of whatever this thing, CX, whatever it is, what should you know? What should you know about like what a bug is? What is the intuition about bugs? What's the intuition about, software testing? What is it? What is it? These are things which are, they're not, I mean, those are things which have gotten taught in computer science as part of the trade of programming, but kind of the conceptual points about what these things are. It surprised me just at a very practical level. I wrote this little explainer thing about ChatGPT, and I thought, well, I'm writing this partly because I wanted to make sure I understood it myself, and so on. And it's been, it's been really popular, and surprisingly so. And then I realized, well, actually, I was sort of assuming, I didn't really think about it, actually. I just thought this is something I can write. And I realized, actually, it's a level of description that is kind of, what has to be, it's not the engineering level description. It's not the kind of just the qualitative kind of description. It's some kind of sort of expository, mechanistic description of what's going on, together with kind of the bigger picture of the philosophy of things and so on. And I realized, actually, this is a pretty good thing for me to write. I kind of know those things. And I kind of realized it's not a collection of things that, I was sort of a little shocked that it's as much of an outlier in terms of explaining what's going on as it's turned out to be. And that makes me feel more of an obligation to kind of write the kind of, what is this thing that you should learn about the computationalization, the formalization of the world? Because, I've spent much of my life working on the kind of tooling and mechanics of that and the science you get from it. So I guess this is my kind of obligation to try to do this. But I think, so if you ask what's going to happen to like the computer science departments and so on, there's some interesting models. So for example, let's take math. Math is a thing that's important for all sorts of fields, engineering, even, chemistry, psychology, whatever else. And I think different universities have kind of evolved that differently. I mean, some say all the math is taught in the math department. And some say, well, we're going to have a math for chemists or something that is taught in the chemistry department. And I think that this question of whether there is a centralization of the teaching of sort of CX is an interesting question. And I think, the way it evolved with math, people understood that math was sort of a separately teachable thing, and was kind of an independent element, as opposed to just being absorbed into now. So if you take the example of writing English or something like this, the first point is that at the college level, at least at fancy colleges, there's a certain amount of English writing that people do, but mostly it's kind of assumed that they pretty much know how to write. That's something they learnt at an earlier stage in education. Maybe rightly or wrongly believing that, but that's different issue. I think it reminds me of my kind of, as I've tried to help people do technical writing and things, I'm always reminded of my 0th law of technical writing, which is if you don't understand what you're writing about, your readers do not stand a chance. Yeah. And so it's I think the thing that has in when it comes to like writing, for example, People in different fields are expected to write English essays, and they're not, mostly the history department or the engineering department. They don't have their own, it's not like it's a thing which sort of people are assumed to have a knowledge of how to write that they can use in all these different fields. And the question is, some level of knowledge of math is kind of assumed by the time you get to the college level, but plenty is not, and that's sort of still centrally taught. The question is sort of how tall is the tower of kind of CX that you need before you can just go use it in all these different fields. And, there will be experts who want to learn the full elaborate tower, and that will be kind of the CS, CX, whatever department. But there'll also be everybody else who just needs to know a certain amount of that to be able to go and do their art history classes and so on.
Yeah, is it just a single class that everybody's required to take?
I don't know. I don't know how big it is yet. I hope to kind of define this curriculum, and I'll figure out whether it's my guess is that I don't know. I don't really understand universities and professoring that well, but my rough guess would be a year of college class will be enough to get to the point where most people have a reasonably broad knowledge of, will be sort of literate in this kind of computational way of thinking about things.
Yeah, basic literacy.
Right.
I'm still stuck, perhaps because I'm hungry, in the rating of human preferences for candy. So I have to ask, what's the best candy? I like this ELO rating for candy. Somebody should come up, because you're somebody who says you like chocolate. What do you think is the best? I'll probably put Milk Duds up there. I don't know if you know. Do you have a preference for chocolate or candy?
Oh, I have lots of preferences. One of my all-time favorites is my whole life is these flake things, Cadbury Flakes, which are not much sold in the US. And I've always thought that was a sign of a lack of respect for the American consumer, because they're these sort of aerated chocolate that's made in a whole sort of it's kind of a sheet of chocolate that's kind of folded up, and when you eat it, flakes fall all over the place.
So it requires a kind of elegance. It requires you to have an elegance.
Well, I know what I usually do is I eat them on a piece of paper or something.
So you embrace the mess and clean it up after.
No, I actually eat the flakes because it turns out the way food tastes depends a lot on its physical structure, and it really I've noticed when I eat pieces of chocolate, I usually have some little piece of chocolate, and I always break off little pieces, partly because then I eat it less fast, but also because it actually tastes different. The small pieces have a different experience than if you have the big slab of chocolate.
For many reasons, yes. Slower, more intimate, because it's
well, I think it's also just pure physicality.
Oh, the texture of it changes.
Yeah, right.
That's fascinating. Now I take back my Milk Duds, because that's such a basic answer. Okay. Do you think consciousness is fundamentally computational? So when you're thinking about CX, what can be turned to computation? And you're thinking about LLMs. Do you think the display of consciousness and the experience of consciousness, the hard problem, is fundamentally a computation?
Yeah, what it feels like inside, so to speak, is, I did a little exercise. Eventually, I'll post it of what it's like to be a computer.
Yeah,
right. It's kind of like, well, you get all this sensory input. You have kind of the way I see it is from the time you boot a computer to the time the computer crashes is like a human life. You're building up a certain amount of state in memory. You remember certain things about your quotes life. Eventually, it's kind of like the next generation of humans is born from the same genetic material, so to speak, with a little bit left on the disk, so to speak. And then the new fresh generation starts up, and eventually all kinds of crud builds up in the memory of the computer, and eventually the thing crashes or whatever, or maybe it has some trauma because you plugged in some weird thing to some port of the computer and that made it crash, and that that's kind of. But you have this picture of from startup to shutdown, what is the life of a computer, so to speak, and what does it feel like to be that computer, and what inner thoughts does it have, and how do you describe it? And it's kind of interesting as you start writing about this to realize it's awfully like what you would say about yourself. That is, it's awfully like even an ordinary computer. Forget all the AI stuff and so on. It's it has a memory of the past. It has certain sensory experiences. It can communicate with other computers, but it has to package up how it's communicating in some kind of language-like form so it can, send, so it can kind of map what's in its memory to what's in the memory of some other computer. It's a surprisingly similar thing. I had an experience just a week or two ago. I'm a collector of all possible data about myself and other things. And so I collect all sorts of weird medical data and so on. And one thing I hadn't collected was I'd never had a whole body MRI scan. So I went and got one of these.
Nice.
Okay, so I get all the data back, right? I'm looking at this thing. I'd never looked at the kind of insides of my brain, so to speak, in physical form. And it's really, it's kind of psychologically shocking in a sense that, here's this thing and you can see it has all these folds and all these, this structure. And it's like, that's where this experience that I'm having of, existing there. And so on, that's where it is. And, it feels very, you look at that and you're thinking, how can this possibly be all this experience that I'm having? And you're realizing, well, I can look at a computer as well. And it's kind of this, I think this idea that you are having an experience that is somehow, transcends the mere sort of physicality of that experience. It's something that's hard to come to terms with, but I think, and I don't think I'm necessarily, my personal experience, I look at the MRI of the brain and then I, know about all kinds of things about neuroscience and all that kind of stuff. And I still feel the way I feel, so to speak. And it sort of seems disconnected, but yet, as I try and rationalize it, I can't really say that there's something kind of different about how I intrinsically feel from the thing that I can plainly see in the sort of physicality of what's going on.
So do you think the computer, a large language model, will experience that transcendence? How does that make you feel? I tend to believe it will.
I think an ordinary computer is already there. I think an ordinary computer is already, it's now a large language model may experience it in a way that is much better aligned with us humans. That is, it's much more, if you could have the discussion with the computer, its intelligence, so to speak, is not particularly well aligned with ours. But the large language model is, it's built to be aligned with our way of thinking about things.
It would be able to explain that it's afraid of being shut off and deleted. It'd be able to say that it's sad of the way you've been speaking to it over the past 2 days.
But that's a weird thing because when it says it's afraid of something, right? We know that it got that idea from the fact that it read on the internet.
Yeah, where did you get it, Stephen? Where did you get it when you say you're afraid?
You are quite. That's the question, right? It's
your parents, your friends,
right? Or my biology. In other words, there's a certain amount that is, the endocrine system kicking in, and these kinds of emotional overlay type things that happen to be that are actually much more physical. Even they're much more sort of straightforwardly chemical than than kind of all of the higher level thinking.
Yeah, but your biology didn't tell you to say "I'm afraid" just at the right time when people that love you are listening, and so you're manipulating them by saying so. That's not your biology. That's
it's
a large language model in that biological neural network of yours.
Yes, but the intrinsic thing of, something sort of shocking is just happening, and you have some sort of reaction, which is, some neurotransmitter gets secreted, and that is the beginning of some, that's one of the pieces of input that then drives. It's kind of like like a prompt for the large language model. Just like when we dream, for example, no doubt there are all these sort of random inputs. They're kind of these random prompts, and then it's percolating through in kind of the way that a large language model does, of kind of putting together things that seem meaningful.
Are you worried about this world where you teach a lot on the internet, and there's people asking questions and comments and so on? You have people that work remotely. Are you worried about this world when large language models create human-like bots that are leaving the comments, asking the questions, or might even become fake employees?
Yeah.
I mean, or worse or better yet, friends of yours.
Right. Look, I mean, one point is my mode of life has been I build tools and then I use the tools.
Yeah.
And in a sense, kind of, I'm building this tower of automation,
Yes.
which, and in a sense, when you make a company or something, you are making sort of automation, but it has some humans in it.
Yes.
But also, as much as possible, it has computers in it. And so I think it's sort of an extension of that. Now, if I really didn't know that, it's a funny question. I mean, it's a funny issue when, if we think about sort of what's going to happen to the future of kind of jobs people do and so on, and there are places where kind of having a human in the loop, there are different reasons to have a human in the loop. For example, you might want a human in the loop because you want another human to be invested in the outcome. You want a human flying the plane who's going to die if the plane crashes along with you, so to speak. And that gives you sort of confidence that the right thing is going to happen. Or you might want, right now, you might want a human in the loop in some kind of sort of human encouragement, persuasion type profession. Whether that will continue, I'm not sure for those types of professions, because it may be that the greater efficiency of being able to have sort of just the right information delivered at just the right time will overcome the kind of oh yes, I want a human there.
Yeah, imagine like a therapist, or even higher stake, like a suicide hotline operated by a large language model.
Yeah.
Oh boy, it's a pretty high stakes situation.
Right. But I mean, it might in fact do the right thing.
Yeah.
Because it might be the case that and that's really partly a question of sort of how complicated is the human. One of the things that's always surprising in some sense is that sometimes human psychology is not that complicated in some sense.
You wrote the blog post, The 50-Year Quest, My Personal Journey. Good title. My Personal Journey with a Second Law of Thermodynamics. So what is this law, and what have you understood about it in the 50-year journey you had with it?
Right. So second law of thermodynamics, sometimes called law of entropy increase, is this principle of physics that says, well, my version of it would be things tend to get more random over time. A version of it that there are many different sort of formulations of it that are things like heat doesn't spontaneously go from a hotter body to a colder one. When you have mechanical work kind of gets dissipated into heat. You have friction and kind of when you systematically move things, eventually there'll be sort of the energy of moving things gets kind of ground down into heat. So people first sort of paid attention to this back in the 1820s when steam engines were a big thing. And the big question was, how efficient could a steam engine be? And there's this chap called Sadi Carnot, who was a French engineer. Actually, his father was a sort of elaborate mathematical engineer in France. But he figured out this kind of rules for how kind of the efficiency of the possible efficiency of something like a steam engine. And in sort of a side part of what he did was this idea that mechanical energy tends to get dissipated as heat, that you end up going from sort of systematic mechanical motion to this kind of random thing. Well, at that time, nobody knew what heat was. At that time, people thought that heat was a fluid, like they called it caloric. And it was a fluid that kind of was absorbed into substances. And when one hot thing would transfer heat to a colder thing, that this fluid would flow from the hot thing to the colder thing. Anyway, then by the 1860s, people had kind of come up with this idea that systematic energy tends to degrade into kind of random heat that could then not be easily turned back into systematic mechanical energy. And then that quickly became sort of a global principle about how things work. The question is, why does it happen that way? So, let's say you have a bunch of molecules in a box, and these molecules are arranged in a very nice sort of flotilla of molecules in one corner of the box. And then what you typically observe is that after a while, these molecules will be kind of randomly arranged in the box. The question is, why does that happen? And people for a long, long time tried to figure out, is there, from the laws of mechanics that determine how these molecules, let's say these molecules are like hard spheres bouncing off each other, from the laws of mechanics that describe those molecules, can we explain why it tends to be the case that we see things that are orderly sort of degrade into disorder? We tend to see things that, you scramble an egg. You take something that's quite ordered and you disorder it, so to speak. That's a thing that sort of happens quite regularly. Or you put some ink into water and it will eventually spread out and fill up, fill up the water. But you don't see those little particles of ink in the water all spontaneously kind of arrange themselves into a big blob and then, jump out of the water or something. So the question is, why do things happen in this kind of irreversible way where you go from order to disorder? Why does it happen that way? And so throughout, in the later part of the 1800s, a lot of work was done on trying to figure out, can one derive this principle, this second law of thermodynamics, this law about the dynamics of heat, so to speak, can one derive this from some fundamental principles of mechanics? In the laws of thermodynamics, the first law is basically the law of energy conservation, that the total energy associated with heat plus the total energy associated with mechanical kinds of things plus other kinds of energy, that total is constant. And that became a pretty well understood principle. But the second law of thermodynamics was always mysterious. Like, why does it work this way? Can it be derived from underlying mechanical laws? And so when I was 12 years old, actually, I had gotten interested. I've been interested in space and things like that because I thought that was kind of the future and interesting sort of technology and so on. And for a while, kind of, every deep space probe was sort of a personal friend type thing. And I knew all kinds of characteristics of it, and was kind of writing up all these things when I was, 8, 9, 10 years old and so on. And then I got interested, from being interested in kind of spacecraft, I got interested in like, how do they work, what are all the instruments on them and so on. And that got me interested in physics, which was just as well, because if I'd stayed interested in space in the mid to late 1960s, I would have had a long wait before space really blossomed as an area. But
timing is everything.
Right. I got interested in physics, and then, the actual sort of detailed story is when I kind of graduated from elementary school at age 12. That's the time when in England where you finish elementary school. I sort of my gift, sort of I suppose more or less for myself, was I got this collection of physics books, which was some course of college physics books, and volume 5 about statistical physics. It has this picture on the cover that shows a bunch of kind of idealized molecules sitting in one side of a box, and then it has a series of frames showing how these molecules sort of spread out in the box. And I thought, that's pretty interesting. What causes that? And read the book, and the book actually, one of the things that was really significant to me about that was the book kind of claimed, although I didn't really understand what it said in detail, it kind of claimed that this sort of principle of physics was derivable somehow. And, other things I'd learnt about physics, it was all like, it's a fact that energy is conserved. It's a fact that relativity works or something. Not, it's something you can derive from some fundamental sort of, it has to be that way as a matter of kind of mathematics or logic or something. So it was sort of interesting to me that there was a thing about physics that was kind of inevitably true and derivable, so to speak. And so I think that, so then I was like, this picture on this book, and I was trying to understand it. And so that was actually the first serious program that I wrote for a computer, was probably 1973, written for this computer the size of a desk, program with paper tape and so on. And I tried to reproduce this picture on the book, and I didn't succeed.
What was the failure mode there? Like, what do you mean you didn't succeed? So it's a bunch
It
of little...
didn't look like... Okay, so what happened is, many years later, I learned how the picture on the book was actually made, and that it was actually kind of a fake. But I didn't know that at that time. And that picture was actually a very high-tech thing when it was made in the beginning of the 1960s. It was made on the largest supercomputer that existed at the time, and even so, it couldn't quite simulate the thing that it was supposed to be simulating. But anyway, I didn't know that until many, many, many years later. So at the time, it was like you have these balls bouncing around in this box, but I was using this computer with 8 kilowords of memory. They were 18-bit words, of memory words, okay? So it was, 24 kilobytes of memory. And it had, it had these instructions. I probably still remember all of its machine instructions. It didn't really like dealing with floating point numbers or anything like that. And so I had to simplify this model of particles bouncing around in a box. And so I thought, well, I'll put them on a grid, and I'll make the things just sort of move one square at a time and so on. And so I did the simulation. And the result was it didn't look anything like the actual pictures on the book. Now, many years later, in fact, very recently, I realized that the thing I'd simulated was actually an example of a whole sort of computational irreducibility story that I absolutely did not recognize at the time. At the time, it just looked like it did something random and it looks wrong, as opposed to it did something random and it's super interesting that it's random. But I didn't recognize that at the time. And so as it was at the time, I got interested in particle physics, and I got interested in other kinds of physics. But this whole second law of thermodynamics thing, this idea that sort of orderly things tend to degrade into disorder, continued to be something I was really interested in. And I was really curious, for the whole universe, why doesn't that happen all the time? Like, we start off in the Big Bang at the beginning of the universe was this thing that seems like it's this very disordered collection of stuff, and then it spontaneously forms itself into galaxies and creates all of this complexity and order in the universe. And so I was very curious how that happens, but I was always kind of thinking this is kind of somehow the second law of thermodynamics is behind it, trying to sort of pull things back into disorder, so to speak. And how was order being created? And so actually I was interested, this is probably now 1980, I got interested in kind of this, galaxy formation and so on in the universe. I also at that time was interested in neural networks, and I was interested in kind of how brains make complicated things happen and so on.
Okay, wait. What's the connection between the formation of galaxies and how brains make complicated things happen?
Because they're both a matter of how complicated things come to happen.
From simple origins.
Yeah, from some sort of known origins. I had the sense that what I was interested in was kind of in all these different cases of where complicated things were arising from rules. Mm-hmm. And, I also looked at snowflakes and things like that. I was curious in fluid dynamics in general. I was just sort of curious about how does complexity arise? And the thing that I didn't, it took me a while to kind of realize that there might be a general phenomenon. I sort of assumed, there's galaxies over here, there's brains over here, they're very different kinds of things. And so what happened, this is probably 1981 or so, I decided, okay, I'm going to try and make the minimal model of how these things work.
Yes.
And it was sort of an interesting experience because I had built, starting in 1979, I built my first big computer system, a thing called SMP, Symbolic Manipulation Program. It's kind of a forerunner of modern Wolfram language, with many of the same ideas about symbolic computation and so on. But the thing that was very important to me about that was, in building that language, I had basically tried to figure out what were the relevant computational primitives, which have turned out to stay with me for the last 40-something years. But it was also important because in building a language was a very different activity from natural science, which is what I'd mostly done before. Because in natural science, you start from the phenomena of the world and you try and figure out, so how can I make sense of the phenomena of the world? And, kind of the world presents you with what it has to offer, so to speak, and you have to make sense of it. When you build computer language or something, you are creating your own primitives, and then you say, so what can you make from these? Sort of the opposite way around from what you do in natural science. But I'd had the experience of doing that, and so I was kind of like, okay, what happens if you sort of make an artificial physics? What happens if you just make up the rules by which systems operate? And then I was thinking, for all these different systems, whether it was galaxies or brains or whatever, what's the absolutely minimal model that kind of captures the things that are important about those systems?
The computational primitives of that system.
Yes. And so that's what ended up with these cellular automata, where you just have a line of black and white cells. You just have a rule that says, given a cell and its neighbors, what will the color of the cell be on the next step? And you just run it in a series of steps. And the ironic thing is that cellular automata are great models for many kinds of things, but galaxies and brains are two examples where they do very, very badly. They're really irrelevant to those two cases.
Is there a connection to the second law of thermodynamics and cellular automata?
Oh, yes.
The things you've discovered about cellular automata.
Yes. Okay, so when I first started studying cellular automata, my first papers about them were, the first sentence was always about the second law of thermodynamics. It was always about how does order manage to be produced, even though there's a second law of thermodynamics which tries to pull things back into disorder. And my early understanding of that had to do with these are intrinsically irreversible processes in cellular automata that form, can form orderly structures even from random initial conditions. But then what I realized, this was, it's one of these things where it was a discovery that I should have made earlier but didn't. So, in studying cellular automata, what I did was the sort of most obvious computer experiment. You just try all the different rules and see what they do. It's kind of like, you've invented a computational telescope, you just point it at the most obvious thing in the sky, and then you just see what's there. And so I did that, and I, was making all these pictures of how cellular automata work, and I studied these pictures, I studied in great detail. You can number the rules for cellular automata, and one of them is, Rule 30. So I made a picture of Rule 30 back in 1981 or so. And Rule 30, well, at the time I was just like, okay, it's another one of these rules. It happens to be asymmetric, left-right, asymmetric. And it's like, let me just consider the case of the symmetric ones just to keep things simpler, et cetera, et cetera, et cetera. And I just kind of ignored it. Yeah. And then sort of in 1984, strangely enough, I ended up having an early laser printer, which made very high-resolution pictures. And I thought, I'm going to print out an interesting, I want to make an interesting picture. Let me take this Rule 30 thing and just make a high-resolution picture of it. Mm-hmm. And I did, and it has this very remarkable property that its rule is very simple. You started off just from one black cell at the top, and it makes this kind of triangular pattern. But if you look inside this pattern, it looks really random. There's, you look at the center column of cells, and, I studied that in great detail, and so far as one can tell, it's completely random. And it's kind of a little bit like digits of pi. Once you know the rule for generating the digits of pi, but once you've generated them, 3.14159, etc., they seem completely random. Mm-hmm. And in fact, I put up this prize back in, 2019 or something, for prove anything about this sequence, basically.
Has anyone been able to do anything on that?
People have sent me some things, but it's, I don't know how hard these problems are. I mean, I was kind of spoiled because 2007, I put up a prize for determining whether a particular Turing machine that I thought was the simplest candidate for being a universal Turing machine, determine whether it is or isn't a universal Turing machine. Mm-hmm. And somebody did a really good job of winning that prize and proving that it was a universal Turing machine in about 6 months. And so I didn't know whether that would be one of these problems that was out there for hundreds of years, or whether in this particular case, a young chap called Alex Smith, nailed it in 6 months. And so with this Rule 30 collection, I don't really know whether these are things that are 100 years away from being able to get, or whether somebody's going to come and do something very clever.
It's it's like Fermat's last theorem. It's Rule 30 is such a simple formulation. It feels like anyone can look at it, understand it, and feel like it's within grasp to be able to predict something, to derive some kind of law that allows you to predict something about this middle column of Rule 30.
Right. But, this is...
And yet you can't.
Yeah, right. this is the intuitional surprise of computational irreducibility and so on, that even though the rules are simple, you can't tell what's going to happen and you can't prove things about it. And I think, so anyway, the thing, I sort of started in 1984 or so, I started realizing there's this phenomenon that you can have very simple rules, they produce apparently random behavior. Okay, so that's a little bit like the second law of thermodynamics, because it's like you have this simple initial condition, you can, readily see that it's very, you can describe it very easily, and yet it makes this thing that seems to be random. Now, turns out there's some technical detail about the second law of thermodynamics and about the idea of reversibility. When you have if you have kind of a movie of two, billiard balls colliding, and you see them collide and they bounce off, and you run that movie in reverse, you can't tell which way was the forward direction of time and which way was the backward direction of time when you're just looking at individual billiard balls. By the time you've got a whole collection of them, a million of them or something, then it turns out to be the case, and this is the sort of the mystery of the second law, that the orderly thing, you start with the orderly thing and it becomes disordered, and that's the forward direction in time. And the other way round of it starts disordered and becomes ordered, you just don't see that in the world. Now, in principle, if you sort of traced the detailed motions of all those molecules backwards, you would be able to, it will, the reverse of time makes, as you go forwards in time, order goes to disorder. As you go backwards in time, order goes to disorder.
Perfectly so, yes.
Right. So the mystery is, why is it the case that, or one version of the mystery is, why is it the case that you never see something which happens to be just the kind of disorder that you would need to somehow evolve to order? Yeah. Why does that not happen? Why do you always just see order goes to disorder, not the other way around? So the thing that I kind of realized, I started realizing in the 1980s, is kind of like, it's a bit like cryptography. It's kind of like you start off from this key that's pretty simple, and then you kind of run it, and you can get this, complicated random mess. Mm-hmm. And the thing that I sort of started realizing back then was that the second law is kind of a story of computational irreducibility. It's a story of, what seems, what we can describe easily at the beginning, we can only describe with a lot of computational effort at the end. Okay, so now we come many, many years later, and I was trying to sort of, having done this big project to understand fundamental physics, I realized that sort of a key aspect of that is understanding what observers are like. And then I realized that the second law of thermodynamics is the same story as a bunch of these other cases. It is a story of a computationally bounded observer trying to observe a computationally irreducible system. So it's a story of, underneath the molecules are bouncing around. They're bouncing around in this completely determined way, determined by rules. But the point is that we, as computationally bounded observers, can't tell that there were these sort of simple underlying rules. To us, it just looks random. And when it comes to this question about, can you prepare the initial state so that, the disordered thing is, you have exactly the right disorder to make something orderly, a computationally bounded observer cannot do that. We'd have to have done all of this sort of irreducible computation to work out very precisely what this disordered state, what the exact right disordered state is, so that we would get this ordered thing produced from it.
What does it mean to be computationally bounded observer?
So
Observing a computationally reducible system. So the computationally bounded, is there something formal you can say there?
right. So it means, okay, you can talk about Turing machines, you can talk about computational complexity theory, and polynomial time computation and things like this. There are a variety of ways. So
Observing a computationally reducible system. So the computationally bounded, is there something formal you can say there?
right. So it means, okay, you can talk about Turing machines, you can talk about computational complexity theory, and polynomial time computation and things like this. There are a variety of ways to make something more precise, but I think it's more useful. The intuitive version of it is more useful, which is basically just to say that, how much computation are you going to do to try and work out what's going on? And the answer is, you're not allowed to do we're not able to do a lot of computation. When we've got, in this room, there will be a trillion molecules, a little bit less.
It's a big room.
Right. And, at every moment, every microsecond or something, these molecules are colliding, and that's a lot of computation that's getting done. And the question is, in our brains, we do a lot less computation every second than the computation done by all those molecules. If there is computational irreducibility, we can't work out in detail what all those molecules are going to do. What we can do is only a much smaller amount of computation. And so the second law of thermodynamics is this kind of interplay between the underlying computational irreducibility and the fact that we, as preparers of initial states or as measurers of what happens, are not capable of doing that much computation. So to us, another big formulation of the second law of thermodynamics is this idea of the law of entropy increase.
The characteristic that this universe, the entropy seems to be always increasing. What does that show to you about the evolution of
Well, okay, so first of all, we have to say what entropy is.
Yes.
Okay, and that's very confused in the history of thermodynamics, because entropy was first introduced by a guy called Rudolf Clausius, and he did it in terms of heat and temperature. Okay, subsequently, it was reformulated by a guy called Ludwig Boltzmann, and he formulated it in a much more kind of combinatorial type way. But he always claimed that it was equivalent to Clausius's thing, and in one particular simple example, it is. But that connection between these two formulations of entropy, they've never been connected. I mean, there's really... So the more general definition of entropy, due to Boltzmann, is the following thing. So you say, I have a system, and it has many possible configurations. Molecules can be in many different arrangements, et cetera, et cetera, et cetera. If we know something about the system, for example, we know it's in a box, it has a certain pressure, it has a certain temperature, we know these overall facts about it. Then we say, how many microscopic configurations of the system are possible given those overall constraints? And the entropy is the logarithm of that number. That's the definition. And that's the kind of the general definition of entropy that turns out to be useful. Now, in Boltzmann's time, he thought these general definitions of entropy connected. But that connection between... It's very confused in the history of thermodynamics, because entropy was first introduced by a guy called Rudolf Clausius, and he did it in terms of heat and temperature. Okay. Subsequently, it was reformulated by a guy called Ludwig Boltzmann, and he formulated it in a much more kind of combinatorial type way. But he always claimed that it was equivalent to Clausius's thing, and in one particular simple example, it is. But that connection between these two formulations of entropy, they've never been connected. I mean, there's really... So the more general definition of entropy, due to Boltzmann, is the following thing. So you say, I have a system, and it has many possible configurations. Molecules can be in many different arrangements, et cetera, et cetera, et cetera. If we know something about the system, for example, we know it's in a box, it has a certain pressure, it has a certain temperature, we know these overall facts about it. Then we say, how many microscopic configurations of the system are possible given those overall constraints. And the entropy is the logarithm of that number. That's the definition. And that's the kind of the general definition of entropy that turns out to be useful. Now, in Boltzmann's time, he thought these molecules could be placed anywhere you want. He didn't think, but he said, oh, actually, we can make it a lot simpler by having the molecules be discrete. Well, actually, he didn't know molecules existed, right? In his time, 1860s and so on, the idea that matter might be made of discrete stuff had been floated ever since ancient Greek times, but it had been a long time debate about, is matter discrete, is it continuous? At the moment, at that time, people mostly thought that matter was continuous. And it was all confused with this question about what heat is, and people thought heat was this fluid, and it was a big muddle. And but Boltzmann said, let's assume there are discrete molecules. Let's even assume they have discrete energy levels. Let's say everything is discrete. Then we can do sort of combinatorial mathematics and work out how many configurations of these things there would be in the box. And we can compute this entropy quantity. But he said, but of course, it's just a fiction that these things are discrete. So he said, this is an interesting piece of history, by the way, that was at that time. People didn't know molecules existed. There were other hints from looking at kind of chemistry that there might be discrete atoms and so on, just from the combinatorics of, two hydrogens and one oxygen make water, two amounts of hydrogen plus one amount of oxygen together make water, things like this. But it wasn't known that discrete molecules existed. And in fact, the people, it wasn't until the beginning of the 20th century that Brownian motion was the final giveaway. Brownian motion is, you look under a microscope at these little pieces from pollen grains, you see they're being discretely kicked, and those kicks are water molecules hitting them, and they're discrete. In fact, it was really quite interesting history. I mean, Boltzmann had worked out how things could be discrete and had basically invented something like quantum theory in the 1860s. But he just thought it wasn't really the way it worked. And then just a piece of physics history, because I think it's kind of interesting. In 1900, this guy called Max Planck, who'd been a long-time thermodynamics person, everybody was trying to prove the second law of thermodynamics, including Max Planck. And Max Planck believed that radiation, like electromagnetic radiation, somehow the interaction of that with matter was going to prove the second law of thermodynamics. But he had these experiments that people had done on blackbody radiation, and there were these curves, and you couldn't fit the curves based on his idea for how radiation interacted with matter. Those curves, you couldn't figure out how to fit those curves. Except he noticed that if he just did what Boltzmann had done and assumed that electromagnetic radiation was discrete, he could fit the curves. He said, but, this is just it just happens to work this way. Then Einstein came along and said, well, by the way, the electromagnetic field might actually be discrete. It might be made of photons. And then that explains how this all works. And that was, in 1905, that was how that piece of quantum mechanics got started. Kind of interesting piece of history. I didn't know until I was researching this recently. In 1904 and 1903, Einstein wrote 3 different papers. And just sort of well-known physics history. In 1905, Einstein wrote these 3 papers. One introduced relativity theory, one explained Brownian motion, and one introduced basically photons. So kind of a big deal year for physics and for Einstein. But in the years before that, he'd written several papers, and what were they about? They were about the second law of thermodynamics. And they were an attempt to prove the second law of thermodynamics. And they're nonsense. And so I had no idea that he'd done this.
Interesting. Me neither.
And in fact, what he did, those 3 papers in 1905, well, not so much the relativity paper, the one on Brownian motion, the one on photons, both of these were about the story of sort of making the world discrete. And he got that idea from Boltzmann.
Yeah.
But Boltzmann didn't think, Boltzmann kind of died believing, he said, he has a quote actually, in the end, things are going to turn out to be discrete, and I'm going to write down what I have to say about this because eventually this stuff will be rediscovered, and I want to leave, what I can about how things are going to be discrete. But, I think he has some quote about how, one person can't stand against the tide of history in saying that, matter is discrete.
So he's stuck by his guns in terms of matter is discrete.
Yes, he did. And the, what's interesting about this is at the time, everybody, including Einstein, kind of assumed that space was probably going to end up being discrete too. But that didn't work out technically because it wasn't consistent with relativity theory. It didn't seem to be. And so then in the history of physics, even though people had determined that matter was discrete, electromagnetic field was discrete, space was a holdout of not being discrete. And in fact, Einstein, 1916, has this nice letter he wrote where he says, in the end, it will turn out space is discrete, but we don't have the mathematical tools necessary to figure out how that works yet. And so, I think it's kind of cool that 100 years later we do.
Yes, for you, you're pretty sure that at every layer of reality, it's discrete.
Right, and that space is discrete. And that and in fact, one of the things I realized recently is this kind of theory of heat that that heat is really this continuous fluid. It's kind of like the caloric theory of heat, which turns out to be completely wrong because actually heat is the motion of discrete molecules. Mm-hmm. But unless you know there are discrete molecules, it's hard to understand what heat could possibly be. Well, I think space is discrete. And the question is kind of what's the analog of the mistake that was made with caloric in the case of space? Mm-hmm. And so my current guess is that dark matter is, my little sort of aphorism of the last few months has been, dark matter is the caloric of our time. That is, it will turn out that dark matter is a feature of space, and it is not a bunch of particles. At the time when people were talking about heat, they knew about fluids, and they said, well, heat must just be another kind of fluid because that's what they knew about.
Yes.
But now people know about particles, and so they say, well, what's dark matter? It just must be particles.
So what could dark matter be as a feature of space?
Oh, I don't know yet.
All right.
I think the thing one of the things I'm hoping to be able to do is to find the analog of Brownian motion in space. So, in other words, Brownian motion was seeing down to the level of an effect from individual molecules. Mm-hmm. And so in the case of space, most of the things we see about space so far, just everything seems continuous. Brownian motion had been discovered in the 1830s, mm-hmm. and it was only identified what it was the result of by Smoluchowski and Einstein at the beginning of the 20th century. And, dark matter was discovered, that phenomenon was discovered 100 years ago. Mm-hmm. The rotation curves of galaxies don't follow the luminous matter. That was discovered 100 years ago. And I think, that I wouldn't be surprised if there isn't an effect that we already know about that is kind of the analog of Brownian motion that reveals the discreteness of space. And in fact, we're beginning to have some guesses. We have some evidence that black hole mergers work differently when there's discrete space. And there may be things that you can see in gravitational wave signatures and things associated with the discreteness of space. But this is kind of, for me, it's kind of interesting to see this sort of recapitulation of the history of physics where people, vehemently say, matter is continuous, electromagnetic field is continuous. And turns out it isn't true. And then they say space is continuous. But so, entropy is the number of states of the system consistent with some constraint.
Yes.
And the thing is that if you know in great detail the position of every molecule in the gas, the entropy is always zero because there's only one possible state. The configuration of molecules in the gas, the molecules bounce around. They have a certain rule for bouncing around. There's just one state of the gas, evolves to one state of the gas, and so on. But it's only if you don't know in detail where all the molecules are that you can say, well, the entropy increases because the things we do know about the molecules, there are more possible microscopic states of the system consistent with what we do know about where the molecules are. Mm-hmm. And so the question of whether, this sort of paradox in a sense of, if we knew where all the molecules were, the entropy wouldn't increase. There was this idea introduced by Gibbs in the early 20th century, well, actually the very beginning of the 20th century, as a physics professor, an American physics professor, was sort of the first distinguished American physics professor at Yale. And he introduced this idea of coarse graining, this idea that, well, these molecules have a detailed way they're bouncing around, but we can only observe a coarse-grained version of that. Mm-hmm. But the confusion has been nobody knew what a valid coarse graining would be. So nobody knew that whether you could have this coarse graining that very carefully was sculpted in just such a way that it would notice that the particular configurations that you could get from the simple initial condition, they fit into this coarse graining, and the coarse graining very carefully observes that. Why can't you do that kind of very detailed, precise coarse graining? The answer is because if you are a computationally bounded observer and the underlying dynamics is computationally irreducible, that's what defines possible coarse grainings, is what a computationally bounded observer can do. And it's the fact that a computationally bounded observer is forced to look only at this kind of coarse-grained version of what the system is doing. That's why, and because what's going on underneath is it's kind of filling out the different possible. You're ending up with something where the sort of underlying computational irreducibility is if all you can see is what the coarse-grained result is with a sort of computationally bounded observation, then inevitably there are many possible underlying configurations that are consistent with that.
Just to clarify, basically any observer that exists inside the universe is going to be computationally bounded.
No, any observer like us. I don't know. I can't.
When you say like us, what do you mean? What do you mean like us?
Well, humans with finite minds.
You're including the tools of science.
Yeah. I mean, and as we have more precise, and by the way, there are little sort of microscopic violations of the second law of thermodynamics that you can start to have when you have more precise measurements of where precisely molecules are. Right. But for a large scale, when you have enough molecules, we don't have, we're not tracing all those molecules, and we just don't have the computational resources to do that. And it wouldn't be, I think to imagine what an observer who is not computationally bounded would be like, it's an interesting thing because, okay, so what does computational boundedness mean? Among other things, it means we conclude that definite things happen. We take all this complexity of the world and we make a decision. We're going to turn left or turn right. Mm-hmm. And that is kind of reducing all this kind of detail into we're observing it. We're sort of crushing it down to this one thing.
Yeah.
And that if we didn't do that, we wouldn't have all this sort of symbolic structure that we build up that lets us think things through with our finite minds. We'd be instead, we'd be sort of one with the universe.
So content to not simplify.
Yes. If we didn't simplify, then we wouldn't be like us. We would be like the universe, like the intrinsic universe, but not having experiences like the experiences we have, where we, for example, conclude that definite things happen. We sort of have this notion of being able to make sort of narrative statements.
Yeah. I wonder if it's just like you imagined as a thought experiment, what it's like to be a computer. I wonder if it's possible to try to begin to imagine what it's like to be an unbounded computational observer.
Well, okay. So here's how that, I think, plays out.
My brain just broke. Yeah.
So, I mean, in this, we talk about this Roolead, this space of all possible computations.
Yes.
And this idea of, being at a certain place in the Roolead, which corresponds to sort of a certain way of a certain set of computations that you are representing things in terms of. Okay, so as you expand out in the Roolead, as you kind of encompass more possible views of the universe, as you encompass more possible kinds of computations that you can do, eventually you might say that's a real win. We're colonizing the Roolead. We're building out more paradigms about how to think about things. And eventually you might say, we won all the way. We managed to colonize the whole Ruliad. Okay, here's the problem with that. The problem is that the notion of existence, coherent existence, requires some kind of specialization. By the time you are the whole Ruliad, by the time you cover the whole Ruliad, in no useful sense do you coherently exist. So in other words, in the notion of existence, the notion of what we think of as definite existence requires this kind of specialization, requires this kind of idea that we are not all possible things. We are a particular set of things, and that's kind of how we. That's kind of what makes us have a coherent existence. If we were spread throughout the Ruliad, we would not. There would be no coherence to the way that we work. We would work in all possible ways, and that wouldn't be kind of a notion of identity. We wouldn't have this notion of kind of coherent identity.
I am geographically located somewhere exactly, precisely in the Ruliad, therefore I am. Is the Descartes kind of...
Yeah, right. Well, you're in a certain place in physical space, you're in a certain place in Rulial space. And if you are sufficiently spread out, you are no longer coherent, and you no longer have... I mean, in our perception of what it means to exist and to have experience, right. It doesn't happen that way.
So therefore, to exist means to be computationally bounded.
I think so. To exist in the way that we think of ourselves as existing. Yes.
The very act of existence is like operating in this place that's computationally irreducible. So there's this just giant mess of things going on that you can't possibly predict. But nevertheless, because of your limitations, you have an imperative of like, what is it? An imperative or a skill set to simplify, or an ignorance, a sufficient level.
Okay, so the thing which is not obvious is that you are taking a slice of all this complexity, just like we have all of these molecules bouncing around in the room, but all we notice is, the kind of the flow of the air or the pressure of the air. We're just noticing these particular things. And the big interesting thing is that there are rules, there are laws that govern those big things that we observe.
Yeah.
So it's not obvious that would be the case.
Because it doesn't feel like it's a slice.
Yeah, well, right.
It's not a slice.
Well,
it's like an abstraction.
Yes, but I mean the fact that the gas laws work, that we can describe pressure, volume, et cetera, and that we don't have to go down to the level of talking about individual molecules, that is a non-trivial fact. Mm-hmm. And here's the thing exciting thing as far as I'm concerned. The fact that there are certain aspects of the universe, so, we think space is made ultimately these atoms of space and these hypergraphs and so on, and we think that, but we nevertheless perceive the universe at a large scale to be like continuous space and so on. In quantum mechanics, we think that there are these many threads of time, these many threads of history, yet we kind of span. So in quantum mechanics, in our models of physics, there are these. Time is not a single thread. Time breaks into many threads. They branch, they merge, but we are part of that branching, merging universe. Right. And so our brains are also branching and merging. And so when we perceive the universe, we are branching brains perceiving a branching universe.
Yeah.
And so the fact that the claim that we believe that we are persistent in time, we have this single thread of experience, that's the statement that somehow we manage to aggregate together those separate threads of time that are separated in the fundamental operation of the universe. Mm-hmm. So just as in space, we're averaging over some big region of space and we're looking at the aggregate effects of many atoms of space. So similarly, in what we call branchial space, the space of these quantum branches, we are effectively averaging over many different branches of histories of the universe. And so in thermodynamics, we're averaging over many configurations of, many possible positions of molecules.
Yeah.
So what we see here is, so the question is, when you do that averaging for space, what are the aggregate laws of space? When you do that averaging over branchial space, what are the aggregate laws of branchial space? When you do that averaging over the molecules and so on, what are the aggregate laws you get? And this is the thing that I think is just amazingly neat.
That there are aggregate laws at all.
Well, yes, but the question is, what are those aggregate laws?
Yes.
So the answer is, for space, the aggregate laws are Einstein's equations for gravity, for the structure of space-time. For branchial space, the aggregate laws are the laws of quantum mechanics. Branches, we are effectively the operation of the universe. So just as in space, we're averaging over some big region of span. So in quantum mechanics, in our models of physics, there are these. Time is not a single thread. Time breaks into many threads. They branch, they merge, but we are part of that branching, merging universe.
Right.
And so our brains are also branching and merging. And so when we perceive the universe, we are branching brains perceiving a branching universe.
Yeah.
And so the fact that the claim that we believe that we are persistent in time, we have this single thread of experience, that's the statement that somehow we manage to aggregate together those separate threads of time that are separated in the fundamental operation of the universe. So just as in space, we're averaging over some big region of space and we're looking at many the aggregate effects of many atoms of space. So similarly, in what we call branchial space, the space of these quantum branches, we are effectively averaging over many different branches of histories of the universe. And so in thermodynamics, we're averaging over many configurations of many possible positions of molecules.
Yeah.
So what we see here is, so the question is, when you do that averaging for space, what are the aggregate laws of space? When you do that averaging over branchial space, what are the aggregate laws of branchial space? When you do that averaging over the molecules and so on, what are the aggregate laws you get? And this is the thing that I think is just amazingly neat.
That there are aggregate laws at all.
Well, yes, but the question is, what are those aggregate laws?
Yes.
So the answer is, for space, the aggregate laws are Einstein's equations for gravity, for the structure of space-time. For branchial space, the aggregate laws are the laws of quantum mechanics. And for the case of molecules and things, the aggregate laws are basically the second law of thermodynamics. And so that's the things that follow from the second law of thermodynamics. And so what that means is that the three great theories of the question is, when you do that averaging for space, what are the aggregate laws of space? When you do that averaging over branchial space, what are the aggregate laws of branchial space? When you do that averaging over the molecules and so on, what are the aggregate laws you get? And this is the thing that I think is just amazingly neat.
That there are aggregate laws at all.
Well, yes, but the question is, what are those aggregate laws?
Yes.
So the answer is, for space, the aggregate laws are Einstein's equations for gravity, for the structure of space-time. For branchial space, the aggregate laws are the laws of quantum mechanics. And for the case of molecules and things, the aggregate laws are basically the second law of thermodynamics. And so that's the things that follow from the second law of thermodynamics. And so what that means is that the three great theories of 20th century physics, which are basically general relativity, the theory of gravity, quantum mechanics, and statistical mechanics, which is what kind of grows out of the second law of thermodynamics, all three of the great theories of 20th century physics are the result of this interplay between computational irreducibility and the computational boundedness of observers. And, for me, this is really neat, because it means that all three of these laws are derivable. So we used to think that, for example, Einstein's equations were just sort of a wheel-in feature of our universe, that they could be, the universe might be that way, it might not be that way. Quantum mechanics is just like, well, it just happens to be that way. And the second law, people kind of thought, well, maybe it is derivable. Okay? What turns out to be the case is that all three of the fundamental principles of physics are derivable, but they're not derivable just from mathematics. They require, or just from some kind of logic or computation, they require one more thing. They require that the observer, that the thing that is sampling the way the universe works, is an observer who has these characteristics of computational boundedness, of belief and persistence in time. And so that means that it is the nature of the observer, the rough nature of the observer, not the details of, oh, we got two eyes and we observe photons of this frequency and so on, but the kind of the very coarse features of the observer then imply these very precise facts about physics. And I think it's amazing.
So if we just look at the actual experience of the observer, that we experience this reality, it seems real to us. And you're saying because of our bounded nature, it's actually all an illusion. It's a simplification.
Well, yeah, it's a simplification, right? What's
But you don't think a simplification is an illusion?
No, I mean it's well, I don't know. I mean, what's underneath? Okay, that's an interesting question. What's real? And that relates to the whole question of why does the universe exist? And in the notion of existence, the notion of what we think of as definite existence requires this kind of specialization, requires this kind of idea that we are not all possible things. We are a particular set of things, and that's kind of how we. That's kind of what makes us have a coherent existence. If we were spread throughout the Ruliad, we would not. There would be no coherence to the way that we work. We would work in all possible ways, and that wouldn't be kind of a notion of identity. We wouldn't have this notion of kind of coherent identity.
I am geographically located somewhere exactly, precisely in the Ruliad. Therefore, I am. Is the Descartes kind of.
Yeah, right. Well, you're in a certain place in physical space. You're in a certain place in Rulial space. And if you are sufficiently spread out, you are no longer coherent, and you no longer have. I mean, in our perception of what it means to exist and to have experience, right. It doesn't happen that way.
So therefore, to exist means to be computationally bounded.
I think so. To exist in the way that we think of ourselves as existing. Yes.
The very act of existence is like operating in this place that's computationally irreducible. So there's just giant mess of things going on that you can't possibly predict. But nevertheless, because of your limitations, you have an imperative of like, what is it? An imperative or a skill set to simplify? Or an ignorance, a sufficient level?
Okay, so the thing which is not obvious is that you are taking a slice of all this complexity. Just like we have all of these molecules bouncing around in the room, but all we notice is, the kind of the flow of the air or the pressure of the air. We're just noticing these particular things. And the big interesting thing is that there are rules, there are laws that govern those big things that we observe.
Yeah.
So it's not obvious that would be the case.
Because it doesn't feel like it's a slice.
Yeah, well, right.
It's not a slice.
Well,
it's like an abstraction.
Yes, but I mean, the fact that the gas laws work, that we can describe pressure, volume, et cetera, and that we don't have to go down to the level of talking about individual molecules, that is a non-trivial fact. Mm-hmm. And here's the thing that exciting thing as far as I'm concerned. The fact that there are certain aspects of the universe, so, we think space is made ultimately these atoms of space and these hypergraphs and so on, and we think that, but we nevertheless perceive the universe at a large scale to be like continuous space and so on. In quantum mechanics, we think that there are these many threads of time, these many threads of history, yet we kind of span. So in quantum mechanics, in our models of physics, there are these. Time is not a single thread. Time breaks into many threads. They branch, they merge, but we are part of that branching, merging universe. Right. And so our brains are also branching and merging. So when we perceive the universe, we are branching brains perceiving a branching universe.
Yeah.
And so the fact that the